Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Programming the Unix Pipes. Well, this slide shows the agenda of today's session. Dear students, we all know that a pipe is an inter-process communication tool that is used to communicate between two related processes executing on the same machine. We have seen its usage on the shell, and let me move on the Linux terminal first to have a quick recap. Do read the man page from section 7 of the manual pages about pipes, and it says that it is a unidirectional inter-process communication channel. A pipe has a read end and a write end. Data written to the right end of the pipe can be read from the read end of the pipe. Do read this man page whenever you have time, and let us see its usage. I have a file f1.txt in the present working directory. Let's suppose that I just want to count its lines. So what I can do is I can use pipe. I can use it between the cat and the WC process. The output of the cat program will be placed inside the pipe, and the WC program will read its input from the pipe and give the output. Let us see another example. Suppose I want to count the number of lines in the man page of ls, which contains the string ls. So what I can do is I can give this command. The output of the man will be sent to the input of the pipe. The grep program will read its input from the pipe and write its output to this pipe, and this WC program will read its input from the pipe and send its output to stdout. Okay, so let's fall back to the slides. Okay, pipe history goes back to 3rd edition of UNIX in 73. They have no name and can therefore be used only between related processes, which was corrected in 1982 with the addition of named pipes or FIFOs. Dear students, when we say that a pipe is a byte stream, we mean that there is no concept of message boundaries when using a pipe. Each read operation may read an arbitrary number of bytes regardless of the size of bytes written by the writer. Furthermore, the data passes through the pipe sequentially. Bytes are read from a pipe in exactly the order they were written. So it is not possible to randomly access the data in a pipe using lseek. Moreover, the pipes are unidirectional. When a process reads bytes from a pipe, those bytes are removed from the pipe. That is, the pipes have destructive read semantics. And by default, when a process attempts to read from a pipe that is currently empty, the read call blocks until some bytes are written into the pipe. If the right end of the pipe is closed and a process tries to read it, it will receive an end of file character. An important point to note that if two processes try to read from the same pipe, one process will get some of the bytes from the pipe and the other process will get the other bytes. Unless the two processes use some method to coordinate their access to the pipe, the data they read are likely to be incomplete. As far as writing to a pipe is concerned, by default, when a process attempts to write to a pipe that is currently full, the write system call blocks until there is enough space in the pipe. For example, if a process tries to write, say, 1000 bytes, and there is room for 500 bytes only, the call waits until 1000 bytes of space are available. And if the read end of the pipe is closed and a process tries to write, the kernel sends sig pipe to the writer process. As far as the size of the pipe is concerned, the size of the pipe is normally pipe buff bytes, which on Linux is 4096 bytes. And the kernel ensures that this much amount of writing into the pipe are done atomically. Okay, so now we have a general idea of working and use of pipes on the shell. Let us see how we can write our own programs and make them communicate using pipes. Well, we can create a pipe from within a C program using the pipe system call. And creating a pipe is similar to opening two files. A successful call to pipe returns two open file descriptors in the array fd, which is passed as an argument to the pipe system call. The fd sub 0 contains the read descriptor for the pipe, and fd sub 1 contains the write descriptor of the pipe. Well, the pipe2 system call can also be used to create a pipe, which gives us the features like setting the close on exit flag on the pipe descriptor and making the pipe descriptor non-blocking. Okay, so this slide shows you an illustration showing how we can create a pipe. Well, this is the call which is used to create the pipe, and the pipe is created inside the kernel space, and of course it is unidirectional and having two ends, the read end having the descriptor in fd sub 0 and the right end of the pipe is having its descriptor in fd sub 1. If this is the process which makes this call, after this call the ppfdt of this process will look something like this. You can see we have two additional descriptors, 3 and 4. 3 is pointing to the read end of the pipe and 4 is pointing to the right end of the pipe. So creating a pipe is just like opening two files. Well, after creating this pipe, this process writes something onto the right end of the pipe and then read it from the read end of the pipe and then finally displays it on stdout. Let us move on to the Linux terminal and see an example program that will make us understand the use of pipe as discussed on the last slide. Pipe 1.c. Okay, so here we are creating the pipe, and remember the pipe system call if failed returns -1. And after the pipe is created, the process is writing the message in to the right end of the pipe, and then it is reading the message from the read end of the pipe, and then it is displaying that message on stdout, and after that it is entering in a while one loop. Let me compile and run this program. Pipe 1.c. Well, that is great. Hello world using pipe. Now this process is in the while one loop. Let me move on to another terminal and check this out. Okay, so the ID of this process is 6202. Let me show you from the proc directory 6202, the directory fd, the contents of the directory fd. Well, you can see the ppfdt of this process has two additional descriptors, 3 and 4, pointing to the read and write end of the pipe respectively, as I have just said. Fine, let me quit this program. Well, the use of pipe within a single process is almost useless. I've just shown this example being the simplest of all. Let us move back to the slides and Now let us see how can we use a pipe between two related processes, parent and child. So this slide shows you uh, an illustration showing that. Let's suppose we have the user space and we have the kernel space below, and we have a parent process, and this process is going to communicate with a child process using pipe. The first thing this process will do, it will create a pipe. Once it creates a pipe, you see the PPFTT has two more additional entries. FD0 is pointing to the read end of the pipe, FD1 is pointing to the write end of the pipe. So after creating the pipe, this process will fork to create a child process. So here is the child process. And we all know that once a process forks, the PPFTT of the parent is inherited by the child process. So both these PPFTTs are exactly identical. The PPFTT of the child process is also having the descriptor 3, which is pointing to the read end of the pipe, and descriptor 4, which is pointing to the write end of the pipe. Suppose we want that the parent process should read while the child process should, the parent process should write while the child process should read from the pipe. If the child process wants to read from the pipe, it will read from this FD sub 0, and probably this FD1 is not required. So we better close this FD1. Similarly, the parent process is the writer process, so it will write using this FD1 to the right end of the pipe, and it doesn't require this connection. So we'll close FD sub 0 in the parent process. Now you can see we have a communication channel between the parent and the child process. Okay, let us move again on the Linux terminal and see the proof of this concept from a program that is pipe2.c. Okay, so here is the code, which will be very simple to understand. The parent process is first creating the pipe, then it is doing the fork. Since the parent is the writer process, so it will close the read end of the pipe and it will write in the right end of the pipe. And then of course it will wait for the termination of its child. As far as the child code is concerned, since it is a reader process, it will close the right end of the pipe and it will read from the read end of the pipe and display that on std out. So the parent process will send this message to the child, and the child will display this message on std out. Let me compile this program, pipe2.c, and you see it works pretty fine. Well, dear students, over here the parent was the writer process while the child was the reader process. The question is, what if both the processes wants to send and receive data to each other? That is, they want a bi-directional communication channel. Let us move back to the slides again and see how we can do this. Okay, so this slide shows you an illustration showing the bi-directional communication using pipes, and of course we need two pipes for that. So the parent process will create two pipes. We'll have 4 additional descriptors over here, and since the parent process wants to read from this pipe, so this is the connection which is required. The other connection is closed, and since the parent process wants to write to this pipe, so you see this connection while the other connection is closed. So here is the final PPFTT of the parent process with 4 and 5 closed. The child process will have this PPFTT and it will have descriptor 3 and descriptor 6 closed. So after doing all this, you can see the parent process can write something over here and the child process can read something from here. And I'm sorry, this arrow is a bit wrong. this arrow should be pointing towards that side, and this arrow should be pointing towards this side. Let us move once again onto the terminal and see the proof of this concept. Let me clear screen. Let me do vim pipe 3.c. Fine, you can see that the process has created two pipes this time, has done a fork over here, and over here the child code is shown from this place to almost this place. The child is going to read from FD2 sub 0 and it is going to write into FD1 sub 1. So it is closing the remaining two descriptors, reading from FD2 sub 0 and writing to FD1 sub 1. And this is the parent code, closing the unrequired descriptors of the pipe, writing to pipe 2 and reading from pipe 1. That is great. Let me compile and run this program. You see, child process is over here. The parent has sent a message to the child saying, "What is your name, child?" And this is the parent process, and the child has sent its name, Zilaid Mujahid Butt. So that is great. Let us fall back to the slides again. Move ahead. Okay. So let us try writing a program that simulates this shell command, cat f1.txt and pipe wc. Okay, so what we are going to do now is we are going to create a program and we are going to redirect its output to the right end of the pipe. And over here, this program will have its input redirected. The input will be redirected instead of std in, it will be pointing to the read end of the pipe. So the parent process will create the pipe first. It will then do the fork, will close the non-required descriptors, and then it will exit itself with the cat program. Similarly, the child program will redirect its input, close the unrequired descriptor, that is FD1, and then will exit itself with the WC program. So the WC program will have this PPFDT, while the cat program will have this PPFDT. So whenever the cat will send its output to std out, that is descriptor 1, the output will be sent to the right end of the pipe, that is FD sub 1. And whenever this program, that is WC, will try to read from std in, that is descriptor 0, it will instead read from FD sub 0, which is the read end of the pipe. That is great. Let us once again move on to the slides and see the proof of this concept. And I have written a program for that in pipe 4.c. That is great. Right, dear students, you can see the first thing the process is doing is creating the pipe, then doing the fork, and the parent process is redirecting the std out, that is 1, to point to the right end of the pipe. And then it is closing the unrequired descriptor and then calling exec lp with the cat program with the argument of f1.txt. The child process is redirecting its std in, that is descriptor 0, to point to FD sub 0, that is the read end of the pipe. Then it is closing the unrequired descriptor of the pipe and then finally calling exec lp with the wc program. Let us compile and run this code and see what it do. Pipe 4.c ./a.out. That is great. Actually what is happening is it is the replica of this program, cat f1.txt and pipe to wc, the same output. You see this file has 1, 2, 3, 4, 5 lines, 22 words and 122 characters. So dear students, we have successfully communicated between two processes using the pipe. Let us extend this example and try communicating between three processes. For example, let's suppose take the same example, man ls, grep ls and pipe it to wc. And this time let us assume that we have a shell process which wants to run this pipeline chain. So the model it will use will be a process fan. Let us first understand it on the slide using an illustration again, and then we will review the sample code. So let me fall back to the slides. Okay. So over here you see we have a process which is going to do fork 3 times. Remember, the child process will not do a fork, only the parent will do a fork. So this is a process fan. Of course, before doing these 3 forks, the parent process will create 2 pipes. And then it will do the first fork, and in this fork, we are going to exit the main program, and we want to redirect the output of the main program. You can see over here, I have redirected the output of the main program, and the descriptor 1 of this PPFTT is pointing to the right end of this pipe 1 over here. I hope this is making sense to you. Over here, the grep program, we need to redirect the input as well as the output. So you see, this should be the PPFTT of the grep program before we do actually exec lp with the grep. So std in will be pointing to the right end of this pipe, and std out, that is descriptor 1, will be pointing to the right end of this pipe. Finally, the WC program, we just need to do the input redirection. That is descriptor 0 will be pointing to FD2 sub 0, that is the read end of pipe 2. Once all these programs are executing, the parent process must wait for these programs, and finally the parent process will exit. I hope this makes sense. Let me show you the code as well. Pipe 5.c. Okay. So you see the parent process, the main program is actually calling pipe twice, creating 2 pipes. Parent do a first fork to execute the main program. Then parent do a second fork to execute the grep program. And finally parent do a third fork to execute the WC program. And the parent wait for all its 3 children to terminate. Let's see the code of each child program now. So over here, we just need to redirect the output of the main program. So this is what we are doing over here. And we are closing all the remaining 3 descriptors. And then we are going to do exec lp with the main program. And we are giving the command line argument ls to this main program. After this, the parent do a second fork, and this is the grep program. And if I fall back over here, you can see we need to redirect the input as well as output of the grep program. So we are redirecting the std in of grep to fd1 sub 0, and we need to do the redirection of std out of grep to fd2 sub 1, and we are closing the remaining unrequired descriptors of the pipe, and finally we are doing exec lp with the grep command. Finally, the parent do the third fork, and as far as the third program is concerned, we just need to redirect the input as shown over here. We have just redirected the input, close the unrequired descriptors of the pipes, and then calling exec lp with the wc program. Over here only the main program will come, that is the parent program, which will close all the descriptors, as the parent program doesn't need any descriptor of these two pipes, and then it will wait for all its 3 children, and then it will display the message, parent is done. That is great. Let me compile this program, pipe 5.c, and let me run it. So that is great. ls grep ls wc. So far so good. Okay dear students, I think you all have a fair idea now as to how we can use pipes among related processes. Inshallah, in the next session we will see how we can use named pipes, that is FIFOs, to communicate among unrelated processes. If you have liked today's session, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning, and Allah Hafiz.